Hi, this is Chris. The subject of this video is working with shells or plates in ENERCALC 3D. In this video we'll cover four major topics. The first will be adding individual shells on grids. Then we'll talk about proper shell geometry. The third topic will be why we work with a mesh of shells. And then the last topic will be generating many shells by a variety of different commands. So let's first take a look at how we can add an individual shell in ENERCALC 3D. The command that we want is draw shells, which can be launched either from this icon or from draw and then come down to draw shell. Either way we get the pen icon, and when we hover over the grid we can see that the cursor tends to snap to grid intersections with that triangle. So whenever it's hovered over a grid intersection, I can just click the mouse button and notice that I'm working in a counterclockwise direction. Shells can be drawn either clockwise or counterclockwise, but there we have a four-sided, four-noded shell. Now, while we're on the subject of drawing shells individually, let's talk a little bit about proper shell formation. What we really want with a shell is something that's square, ideally. We can't always achieve that, but we shoot for that as a goal. But there are some definite things that we want to try to avoid with shells. One of those things being extremely long, slender shells that are very rectangular, something like this. We'd really like to try to keep those shell aspect ratios down to about 2 to 1. In no case should they exceed 4 to 1 because we can just get erroneous results from the finite element analysis. So a shell like this would be considered way too slender, way too long, and it should be subdivided for more accurate results. The other thing that we want to make sure we do with individual shells is we always want to draw them either in a counterclockwise or a clockwise order. We want to make sure that we don't crisscross. So let me draw a bigger shell here and show what happens if I intentionally go out of order and draw something that's not clockwise or counterclockwise. So this sort of looks like a bow tie. It's what we call a warped plate. It won't function properly. The results can't be trusted. So to avoid those, just always make sure that you draw shells either in a clockwise or a counterclockwise direction, and you won't have a warped shell. The other thing that we want to be careful to avoid is a shell that's warped by having one or more of its nodes in different planes. So we always want to make sure that all four nodes of a quad shell fall in a single plane. So that's a little bit about proper shell formation and geometry. The next thing that we need to discuss is why we always hear of using shells in a mesh. And the reason for that is that the shell will only produce accurate stress results at its geometric center. They can be extrapolated out to the corners, but analytically it's only accurate to produce stresses at its center, and it'll only produce accurate deflections at its nodes. In fact, only produce any deflections at its nodes. So when you think about any real structure that you might want to model as a shell, like a shear wall or a floor, if there's any reason at all why you might want to have stresses at locations other than the geometric center, like for instance if you have a stairwell opening and you'd like to know what the stresses are near that opening that's not near the center, or if you have a shell where you want to determine some deflections along intermediate points at a perimeter, you obviously have a need for centers at locations other than the overall center of the structural element, and you have the need for nodes to be at locations other than at the extreme corners of the structural entity. So these things lead us to want to create meshes of many small finite elements so that we always make sure we have centers of some elements relatively near to where we're interested in stresses, and so that we always have nodes at many intermediate locations along the structural element so that we can determine deflections at points of interest. So with that said, The rest of the video is really about how we can generate not individual shells like these, but instead how we can generate many shells and do that efficiently by creating them all at once. So I'll come up to the model editing item in the menu and just point out that there's an item called Generate, which has an option to generate rectangular shells and circular shells. There's also an option to generate shells by nodes. I won't go into detail on these, but I just want to point out that they're here, and they're all ways that we can create many shells in one step. Also notice that there's a duplicate, which is just copy. That obviously is a way to copy an existing shell or a group of selected shells. And then there's a command called array that lets us generate multiple copies in one step. The command that I'd like to focus on, though, is called submesh shells. This is the one that I find to be most useful in general. And what I'll do to set up for that command is create just one single large element on my grid. Let's assume that this is a floor or a roof, some sort of a plate that we want to study. But again, I've set myself up so that I can't collect much information at this point from an analysis because I only have this one giant shell. So what I can do to fix that is select the shell and then say Model Editing and come down to Submesh Shells. What this lets me do is specify the number of divisions that I want to create along each side. So it refers to side 1, 2, meaning the first and second nodes that I clicked. And it forces the same number of divisions along the opposite side, which would be side 3, 4. And then it lets us specify a different number of divisions along the other two sides. So let's just keep it simple and say that I'd like to create 10 divisions along this grid, and I'd like to do that for both of my directions. I can click OK and acknowledge, and now I have a mesh of 10 by 10 shells with lots more nodes, lots more shells, much finer mesh, so I'll be able to get more precise results for stresses and for deflections at locations all over that mesh. And that tool is useful for shells that are oriented in any direction. So for efficiency's sake, when you're trying to model meshes, think in terms of generating one giant element that borders the mesh and then just subdivide it, and the program takes care of all the numbering and all the connectivities for us. I think you'll find that tool to be very useful. Hopefully all this info has been useful as you go ahead and work with ENERCALC 3D with your finite element meshes.